Welcome back, everybody. Today we're going to be starting a new topic. We're going to be looking at the principle of moments. And by the end of this lesson, hopefully you'll be able to calculate a moment, which is the turning effect of a force, and you'll be able to apply that idea in everyday situations. So this word moment might just have you a little bit dumbfounded at the moment, because you probably think of a moment as being a moment in time, or maybe even kind of like when someone asks you to please wait a moment. But a moment is a science word. What it describes is the turning effect of a force. What I'm going to ask you to do first is go and investigate this very quickly. So I'd like you to go and find the nearest door handle. And what I'd like you to do is I'd like you to press it in two positions. I'd like you to press it in position A, and I'd like you to press it in position B, which is nearer the end of the door handle. And I'd like you to press with the same force on each occasion. Come back and tell me what happened. Okay, so what you probably found is that when you pressed the position B, the door handle was much easier to move than when you pressed the position A. And that's because the moment of position B, the turning effect, was much greater. And the reason for that is a moment depends on two things. It depends on the distance from the pivot, and in position B, you were much further away from the pivot, which is there where the door handle is attached to the door. And it also relies on the force that you applied, and I asked you to apply the same force. If you went back now to the door handle at position A and you press much harder, you would get the door handle to move the same as you would at position B. Moments are everywhere and they make our life much easier, and one place where you've definitely used a moment and had some fun with it would be on a seesaw. And so these two boys are exactly the same distance from the pivot, which is in the middle of the seesaw. And yet it's the boy in blue who is turning the seesaw down on his end, which must mean he's applying a much greater force. Something you will definitely do later in life, if not already, would be to use a screwdriver to put a screw into wood. And in that picture, you can see that the hand that's screwing the screwdriver around is actually quite a long way away from the screw, which is the pivot. And that makes turning that screw into the wood much easier. If you tried that with a much smaller screwdriver, kind of like one of those little screwdrivers you get in a Christmas cracker, it'd be very, very difficult to turn the screw. And the same principle applies when using a spanner. The bigger the spanner, the further away your hand is from the bolt, which is the pivot, the much easier it is to screw something tight or to loosen it. So can we put a number on that? Can we actually prove that position B was a much bigger moment than position A? And we can, because there's a very simple calculation used to calculate the size of a moment. A moment, which is in Newton meters, is equal to the force applied in newtons times the distance from the pivot, which is in meters. So if we go back to the door handle and we think of position B, the distance from the pivot was 0.15 meters, 15 centimeters. And the force that we applied, we'll say, is 4 newtons. So we can calculate the moment really simply. The moment would be equal to 4 newtons, which is the force, times the distance, which is 0.15 meters. And if we put that in the calculator, we can get the moment of 0.6 Newton meters. Really simple equation to use. Can you apply then the moment equation in this question? The question says, a mechanic uses a spanner to release the bolt off a car. The mechanic applies a force of 12 newtons on the spanner at a distance of 17 centimeters from the bolt. What is the size of the moment? Pause the video now and work out your calculation. So, hopefully what you did was work out that the moment is equal to the force, which is 12 newtons, times the distance, which is 17 centimeters. Now that causes a little bit of a problem. If you look at the equation must have the distance in meters, and yet in the question it says 17 centimeters. So we need to convert from centimeters to meters. There are 100 centimeters in 1 meter, so therefore the equation should read 12 newtons times 0.17 meters. So we've converted those centimeters into meters. And if we then put that in a calculator, the answer would be 2.04 Newton meters. If you got the wrong answer, you probably put 204 Newton meters. But hopefully you'll spot that as we go forward. Okay, time for some quick practice. and there are 4 questions on the screen for you to work out. In each of those you have a distance and you have a force. Before you start, just be careful, make sure that the force is in newtons and make sure that the distance is definitely in meters. Pause the video now and try it. Okay, how did you get on? First one's easy. It's 3 newtons times 2.5 meters. The answer is 7.5 newton meters. And the second one is 120 newtons times 1.7 meters, which is 204 newton meters. In the third one, we've got 5 newtons and 20 centimeters. So we need to convert those centimeters into meters. So it'd be 5 newtons times 0.2 meters, which is 1 newton meter. And in the final one, we've got 2 kilonewtons. So there are 1,000 newtons in 1 kilonewton. So therefore, we're going to have 2,000 newtons times 2.2 meters. So the answer is 4,400 newton meters. Well done if you got those right. Okay, so it's time now to apply your understanding of what a moment actually is. So there are 2 different types of tap on the screen. And what I'd like you to do is put yourself in this situation. You're building a care home for elderly people. And I'd like you to tell me, as you're building the bathrooms and the kitchens in that care home, which taps would you choose for the care home? And what I want you to do is explain your answer using the principle of moments. Now, there's no answer on the screen from me today. What I'd like you to do is either write that down and email it to your teacher, or put it on a Google document and also email it to your teacher. Okay, and finally, for a little bit of fun, what I'd like you to do is I'd like you to take a ruler and I'd like you to balance that ruler on a Lego brick or a matchbox or something like that so that it's perfectly level and balanced. Okay, and then what I'd like you to do is I'd like you to find 4 pennies, 4 1p's, and I'd like you to put them at 7 centimeters from the middle, from the pivot. Okay, now if you did that and let go of it, it's obviously going to topple over. So you're going to have to do that and hold it. What I'd then like you to do is 2 centimeters from the pivot, is I'd like you then to find out how many coins, how many 1p coins that is, you would have to put there to make the seesaw balance. Take a picture of it, write your answer down and email it to your teacher. Hope you've enjoyed today's lesson. Take care everybody.